A wave is a continuous disturbance that transfers energy between two locations without transferring matter. So if we look at this simulation of a wave propagating through a string, and I'll link this below in a description so you can experiment with it yourself. So we'll pick the oscillate option, effectively moving one end of the string up and down continuously. And that sends a disturbance in the string. So effectively, if we track one of these particles, so this green particle for example, it moves up and down in the same spot. So there's no particles traveling through the string. Now a wave pulse, on the other hand, is a single disturbance that transfers energy between two locations of the string. So if we move the end of this string up and down once, then we can see the pulse propagating through the string. So a wave is continuous, whereas a pulse is not. And because a wave is periodic, so we can see that it repeats, we can model it as a continuous periodic disturbance with a well-defined wavelength and frequency. So let's have a look at these properties. So if we look at a particle in the string at some position, and if we plot its displacement from the equilibrium position versus time, we see the particle starts at equilibrium, then moves upwards by a certain amount, goes back through equilibrium, and then moves downwards by the same amount, and goes back towards equilibrium. So this marks one cycle. And the time it takes to complete this cycle is called the period of the oscillation. And we can take the period from peak to peak. So for example, where the particle starts from this position and ends up back at this position is the same time that it takes to complete one cycle. Now the frequency of the oscillation is the number of cycles that the particle completes in 1 second. So that has a unit of hertz. And we've seen in the harmonic oscillator that the period is related to the frequency, being the reciprocal of the frequency. Now the wavelength, on the other hand, is obtained if we plot the displacement of the particles in the string versus the position along the string at a particular time. So for example, this here is our string, and as the disturbance moves through the string at some velocity, the particles are going to oscillate in this manner. And in this case, the distance between two particles that are displaced by the same amount is called the wavelength. So that can be the distance between the peaks or the crests. Distance between the troughs is also the wavelength. Or this distance over here is also the wavelength. So basically it's the length of the wave, which is periodic, so it repeats along the string. Now another example of a wave is a sound wave. So for example, if these strings of the guitar are plucked back and forth, they're going to disturb the air particles around them. Then you get a wave propagating through air. So a particle that was here, for example, being the equilibrium position, oscillates between 2 points, and in turn disturbs the air particles around it. So this creates regions of high pressure in the air. So these are the compression regions. And we'll look further into the variations of pressure in a medium due to a sound wave when we'll look at sound waves in more detail. So these two examples of a wave through a string and a sound wave are examples of mechanical waves, or in the case where we're looking at a single pulse, that's called a mechanical wave pulse. So mechanical waves or wave pulses require a medium to propagate. So here sound moves through air and a wave moves through a string. But electromagnetic waves, on the other hand, or light waves, do not require a medium to propagate. So remember that light behaves like a particle and a wave, so it can create its own disturbances. So for example, light going from this flashlight has a wave front that moves in this direction, and the photons oscillate back and forth in the direction perpendicular to the motion of the wavefront, which creates perpendicular electric and magnetic fields. So the electromagnetic wave looks something like this. And we'll also look at electromagnetic waves in more detail. Recall the wave propagating through a string which has some length L, and generally the speed at which the wave or wave pulse propagates through a medium depends on the type of wave and the properties of the medium. So for an electromagnetic wave, the speed of all electromagnetic waves in a vacuum, which is a universal physical constant, is equal to around 3 by 10 to the 8 meters per second, being the speed of light in a vacuum. Now consider our string here and the speed of the wave going through the string. And if we cut out a small part of this string and blow it up here, the length of this section of string is delta L. And we're not doing calculus here, so we'll just assume this is a very small length. So before sending a disturbance through this string, suppose a tension force was applied to the string. And while this tension force was in a string, the string was plucked up and down continuously at one end, and this wave propagated through the string. So therefore, we have the tension force throughout this string being uniform, and then we take the center of curvature of this length of string as C, and the radius of curvature being the distance from C. So the line of the radius of curvature is perpendicular to the arc of the string at this point, and same on this side. And this angle here we take as delta theta, which is equal to this angle. So by geometry, this angle will be delta theta, and so will this angle. And the same on this side. Now if we suppose we're moving along with the wave, so for example, we're standing on this wave and moving along with it, so therefore this element of the string is going to appear to be moving to the left at the same speed as the wave. Now if we take a sum of forces in the horizontal direction, we have minus ft cosine delta theta plus ft cosine delta theta. So given the forces balance, then the string element is in dynamic equilibrium in the horizontal direction. And if we take a sum of forces in the vertical direction, so note that this force, being tangent to the string at this point, is resolved into horizontal and vertical components. And same with the force on this side. So in the vertical direction, this component has a magnitude of Ft sine delta theta. And we have two components of force acting downwards, so we multiply by 2. And we're going to use a small angle approximation, meaning that sine of the angle is approximately equal to that angle for angles much less than 1. So therefore we take sine delta theta as delta theta. And therefore the net force is assumed to act towards the center of curvature for small angles. So as this element of the string moves at some speed, the net force acting on it towards the center of curvature is equal to the mass of this element of string, which we'll take as delta m, by the speed that this element of string is moving relative to our observer that's moving along with the wave at a constant speed. So that's equal to the wave speed squared on the radius of curvature. So note that given our small angle approximation, we assume that the vertical component of force points towards the center of curvature and gives rise to a centripetal acceleration. Now if we multiply through by rho, we have rho by 2 delta theta by the tension force in the string is equal to delta m by the wave speed squared. And by geometry, we can see that rho by 2 delta theta is equal to delta L, which is the arc length of the element of string. So we can replace this with delta L, and solving for the wave speed through the string, we have Vs is the square root of the tension force by delta L on delta M. Or alternatively, we can write this as a square root of the tension force on delta M on delta L. And this is the linear mass density, or mass per unit length of the string, which is typically denoted as mu, being the mass per unit length. So this ratio is equal to m on L, where the mass density is uniform in a string. So we can finally write this expression as m on L. So therefore a higher tension force in a string results in a higher wave speed through the string. And let's have a look at this using our simulation. So if we send a pulse through this string and set the tension in the string to be very low, we can see it's propagating slowly. And if we increase the tension in the string, it gets faster and faster, as expected. In a given medium, the speed of sound increases with the temperature of the medium. So the speed of sound in a gas medium, like air, can be derived using the wave equation, and it's equal to the square root of the adiabatic constant by the universal gas constant by the temperature of the medium over the molecular mass of the medium. So the adiabatic index for air is 1.4, and the universal gas constant is 8.314 joules per mole Kelvin, which you've seen in the thermodynamics part of the course. And the absolute temperature in Kelvin of a medium that has a temperature of 20 degrees Celsius is 293 Kelvin. And the molecular mass of air is around 28.96 grams per mole. So if you converted the molecular mass to kilograms per mole, you'll get the speed of sound in air being around 343 meters per second at a temperature of 20 degrees. Now in a solid, such as steel for example, the speed of sound can also be derived from the wave equation, and that's equal to the square root of the Young's modulus of steel, which is basically the stiffness of the material, on the density. So this generally applies to a solid subjected to a dynamic force along its axis, which causes a disturbance in the material. So the speed of sound through steel is around 5900 meters per second. And for a liquid such as water, the speed of sound is equal to the square root of the bulk modulus on the density. So in water, the speed of sound is around 1480 meters per second. So recall our string example. The higher the tension force in the string, meaning the string is stiffer and doesn't move as much in the vertical direction, the higher the wave speed through the material. And this is similar in concept to the speed of sound, except sound waves can be visualized as pressure waves. So as a sound wave propagates through a medium, and noting that we're looking at this medium at a particular point in time, the particles get bunched up in the compression regions when the sound wave propagates through the medium, and these are the regions where the pressure is the highest. And then in these empty regions, which are called the rarefaction regions, you get a negative pressure, which acts like a vacuum that pulls the particles towards it. So for example, if you vibrate the strings of this guitar, the sound propagates through the medium through the oscillation of the air molecules, which interact with neighboring air molecules to propagate the disturbance. So you get repeated regions of compression and rarefaction, and this disturbance propagates and can be heard at some distance away. So note that the particle itself is not moving from here to the person's ear. The disturbance propagates through the medium, through the interactions between oscillating particles and their neighboring particles. So for example, if you track one particle and take the vertical axis as the displacement of the particle from equilibrium in the horizontal direction, and the horizontal axis as time, then this particle starts at the equilibrium position and oscillates back and forth in a periodic manner. So again, in this type of plot, this distance is the period of the oscillation, and in space, the distance between two compression regions is the wavelength. And a higher temperature, meaning the air particles have a higher average kinetic energy, results in a higher wave speed through the medium. In a transverse wave, such as a light wave for example, where the wavefront propagates in this direction at the speed of light, the direction of the disturbance is perpendicular to the direction that the wave propagates. So for example, if we look at a photon, it's going to oscillate back and forth in the perpendicular directions to the velocity of this wave front. So another example is this wave propagating in water. So for example, if a rock is dropped in a pond, so the wave front is propagating in this direction at some velocity. So at the crest of the wave, we have a water particle that's moved upwards, and at the trough, we have the water particle that's moved downwards. So these are examples of transverse waves. Similar to the disturbance we saw in the string. Now a sound wave is an example of a longitudinal wave. So for example, if a sound wave propagates through air, we see the wave front propagating in this direction, and the sound particles oscillate back and forth in the direction that's parallel to the velocity of the wavefront. So in other words, the direction of the disturbance is parallel to the direction of propagation of the wave. And we model sound waves as mechanical longitudinal waves. So if we look at a snapshot in time and measure the pressure at several points along this line in the medium, we see the variation of pressure with the horizontal position along the medium as periodic. So as we've seen previously, at the high pressure regions, we have compression, and the rarefaction regions are the negative pressure regions. Suppose we have a speaker, and this diaphragm moves back and forth at some amplitude and frequency to cause a sound wave to propagate through an air medium. And using an oscilloscope, we measure the pressure at some point in the medium over time. So as the disturbance propagates through this point, we have the pressure being at the atmospheric pressure, rising due to the air particles being compressed, and then it drops below atmospheric pressure, which we call rarefaction, when the air expands. So therefore the particles oscillate back and forth and interact with the neighboring particles for the disturbance of a sound wave to propagate through this medium. So recall the sound wave is a longitudinal wave, and typically the amplitude of a wave is the maximum displacement of the wave from its equilibrium position. But in the case of a sound wave, being a longitudinal pressure wave, the amplitude can be determined by the maximum increase or decrease in pressure from the equilibrium pressure. So in this case, we see the pressure wave is periodic, and the amplitude of the oscillation is measured from equilibrium to the maximum pressure or the minimum pressure. So if the diaphragm of this speaker oscillates with a higher amplitude, then an increasing amplitude increases the loudness of the sound, which is heard at another point in the medium. So loudness increases with an increase in amplitude. Now on the other hand, the pitch of the sound increases with frequency. So if the diaphragm of this speaker oscillates back and forth faster, then we get a higher pitch. So for example, and for a lower frequency, the pitch decreases, which will sound something like this. Now the energy carried by a wave increases with an increasing amplitude, and specifically is proportional to the squared amplitude. So for our wave propagating on a string, we can determine the total energy of the wave as the kinetic plus the potential energy, and you'll need calculus to derive it using the solution to the wave equation, which is beyond the scope of this course, but we'll just interpret the result for a travelling wave in a string. So we have 1/2 by the linear density multiplied by the square of the frequency of the oscillation multiplied by the squared amplitude by the wavelength. So remember that the frequency is the reciprocal of the period. So the lower the period of the oscillation, the higher the frequency, and the higher the energy carried by the wave. And similarly, a higher amplitude means that the wave carries more energy.